we introduce a graph-based solution to general surface normal integration. This project is a collaborative effort between researchers from University of Oxford, Peking University, and the National Institute of Informatics in Tokyo. Surface normal integration takes a set of points with given per-point orientations and their corresponding x and y coordinates in camera coordinate system as input and predicts per-point depth values. In many practical scenarios, depth discontinuities pose a major challenge to this inverse problem. To address this, we must correctly identify how each point correlates with its neighboring points. The primary goal of our work is to formulate these per-point correlation patterns into a graph-based objective function and design a numerical optimizer capable of minimizing it. We propose treating an arbitrary, semi-differentiable surface as a weighted graph. Here, the points sampled from the surface serve as graph nodes, and each directional edge weight is evaluated in terms of point-to-plane distance. Specifically, a tangent plane is extended from each point, and the total derivative dictates how well its neighboring points fit this local plane. The magnitude of this distance directly measures the differentiability of the local surface patch. To identify directional non-differentiability, we analyze the configuration of per-point triplets, which are formed by a center point and two of its neighbors. We require that the pair of neighboring points be well separated angularly, and we model the two per-edge distances using a two-component Gaussian mixture. This model guarantees that the center node remains correlated with at least one of its neighbors. Furthermore, equal correlation indicates that the surface is fully differentiable from both sides. The triplet configurations are sampled dynamically based on the current structure of the point cloud. Because a total derivative possesses 2 degrees of freedom, we must sample at least 2 linearly independent triplets for each point to sufficiently characterize the local surface geometry. And our sampling strategy proceeds as follows. First, the edge with the minimum point-to-plane distance is selected. Based on this edge, a second edge with the widest angular separation is chosen to form the first triplet. The second triplet is then formed by maximizing its angular separation relative to the first. This process is repeated to sample additional triplets as needed. Each triplet yields a system of 2 equations solved in a weighted least squares sense. The weights are determined by the output of the two-component Gaussian mixture, ensuring they always sum to 1. Because a global depth offset always exists, this local system is inherently ill-posed. To resolve this, the system is transformed into a global Poisson system and solved efficiently using the conjugate gradient method. The edge weights and per-node depths are obtained jointly by minimizing the weighted point-to-plane distances specified by all sampled triplet configurations. This optimization process consists of 2 alternating stages, shape inference and depth estimation. In the first stage, based on the current estimation of the object shape, triplets are dynamically sampled and their respective edge weights are determined. In the subsequent stage, a large, sparse Poisson system is established to estimate graph-wide depth consistently. After each iteration, each point is relocated to a new position that is more compatible with its neighbors, thereby minimizing the point-to-plane distance. We evaluated our method under both perspective and orthographic projections. Under orthographic projection, we applied our method to objects from the Diligent dataset using both grid and scattered representations. The experiments demonstrate high accuracy and show that the method performs consistently when objects are observed from different viewing angles. Furthermore, our ablation studies validate the effectiveness of triplet sampling in successfully handling depth discontinuities within scattered representations. We also benchmarked the proposed method under perspective projections, evaluating the performance using absolute depth error for direct comparison. Finally, we visualized the dynamics of the optimizer. As demonstrated, both the shape and normal estimates converge promptly, and the exact locations of depth discontinuities are correctly identified. Our code and experimental data will be released on our website. Thank you for your time.